Good afternoon, everyone. Today we have with us Professor Nikita Agarwal, who is a professor in the Department of Mathematics at IISER Bhopal. Professor Nikita Agarwal completed her bachelor's degree in mathematics from Lady Shri Ram College for Women, Delhi University, and her master's and PhD in mathematics from University of Houston, Texas. Her research focuses on dynamical systems and ergodic theory. In today's talk, she will be discussing the mathematical concepts behind fractals, which we often observe in nature. Let's give a warm welcome to Professor Agarwal.
Thank you, Pradipta. I first thank the organizers Siva, Dootika, and Rhythm for inviting me here to interact with this audience. So, the best questions that I hear these days is from my 5-year-old son, who asks me questions which many of them I can't answer immediately. And, uh, and this group of students also fall in a category where you're still exploring things, you're still learning new things, so you have fresh ideas, you have fresh questions, and it's very exciting to know more uh, about anything that we observe. So I'm going to talk about the buzzword, which is fractals, which I think, who has not heard of fractals? Can you raise your hand? So all of you have heard of fractal in some way, right? So you are raising your hand. You have not heard of fractal? Okay, so I have one person who will really be looking forward to all of my slides. So, okay, let us look at these pictures. So because this talk is being recorded, I must say that I have borrowed many of these pictures from the internet. That's the disclaimer. And so what do you see common in all these pictures? Patterns. They're all from nature, right? These are all pictures from nature, what we see in nature, and we see patterns, right? What kind of patterns? What do you mean by patterns? So for example, if you see this floor in this room, do you see patterns? Yes. Are these patterns different from these patterns? In which way? Sorry? They're more intricate, okay. This is very monotonous, right? What you see on the floor. So in nature, you don't see things being monotonous, right? They are intricate, there are so many details, right? And they also teach you the concept of infinity, right? Because as you keep on zooming in and in and in, you see similar structures happening again and again, right? So if you ask a small kid to draw a hill, right, a picture of a hill, you get more or less similar pictures, right? The shape could be a little off, but it looks similar, right? Tree, it looks similar. Leaf, it looks similar, right? So they are able to catch the overall pattern behind all these objects, right? That's what even as a small child you can pick up. So then there is another picture which is from a chemistry lab where again it's a reaction diffusion of two chemicals and you see patterns emerging, right? And it's a very common phenomenon in labs. Then you also have such patterns, such structures inside our body, right? There are 3 such examples here of bronchial tree, renal, vascular, and urinary systems, and heart system, right? Then in soap bubbles, right? And when you look at boundary of any nation, for instance, then again you see patterns, right? So can somebody say what do you see? What is the kind of pattern that you see on the boundary of our country, let's say? Is it smooth? It's rough, right? So you have some experience with differentiability, right? So do you think the curve, if I think of it as a curve, do you think it is differentiable? Right? Doesn't look like, isn't it? So there are two key properties that we are grabbing from here. One is that as you keep on zooming in and in and in, you see similar things happening. Second is you don't see smoothness, right? And that's what is the primary defining feature of a fractal. I'm not saying this is the definition of a fractal from mathematics point of view, but we understand fractals in this way. When an object which appears self-similar upon magnification at various scales, so if you keep on zooming in on the boundary of a country, you see similar patterns, or if you look at hillside and you keep on zooming in, you again see more and more hills, similar structures, right? And each smaller part of the object resembles the entire object. Okay, so these are the two takeaway messages from the pictures that we saw earlier. And key features, as I just mentioned, is self-similarity. I'm not saying the exact replica, okay, but they look similar. And non-differentiability that you see, okay? Okay, let us talk about some man-made fractals. So do you have some examples? Mandelbrot set, the famous Mandelbrot set. Anything else from yesterday's popular talk? Snowflake, right? Anything else that you know of? Man-made meaning I'm constructing it. I have an algorithm to construct. Any other example? Okay, so let me talk about some examples, and I'm going to talk about snowflake as well. Okay, but the first example that I'm going to talk about, which is actually one of the first examples that came about from mathematics, is known as Cantor's set. Okay, and what is Cantor's set? So you start with closed interval 0, 1. Okay, you divide it into 3 equal parts. So 0, 1 by 3, 1 by 3, 2 by 3, 2 by 3, 1. And you remove the middle part, 1 by 3, 2 by 3. Okay, so your starting point is the big interval. That's my first iteration. Like you're talking about iterative scheme, right? I'm giving you an iterative scheme. My first iteration is the interval. Second is these two intervals. So you have a union of two intervals. In the next step, those two intervals that I have, what are the lengths of those two intervals that are left? 1 by 3. You further divide them into 3 parts. So what will be the length of each part? 1 by 9. You drop the middle part. Okay? So the next iteration will be 4 intervals, right? Each having length 1 by 9. And you do this again and again. So in the next step, because you have 4 intervals, you divide all of them into 3 parts, remove the middle parts. How many intervals will be there? Each gives you 2, right? So it is how many? 8, right? In the next step? Okay, so you know what's going on, right? So at every step, each interval in the previous gives you 2. So it's 2 times what you have before that, right? And you look at the limit of this. Now you are talking about limits of points, right? I give you sequence of points and you can make sense of limit of a sequence of points. Now they are no longer points, single points, they are collection of points. So it's an interval, 2 intervals, 4 intervals, and so on. So it should converge to a set, right? Do you think that set would be non-empty? You're taking away things every time, right? So you're shrinking the intervals that are remained, right? That are left behind. So do you think anything will be left at the end? So 0 and 1 will definitely be retained, right? Because when you are trisecting the interval, endpoints which are on the left and the right will always be there. So 2 points are for sure there, which are 0 and 1, right? So it's a non-empty set. Is it a finite set? No. Infinitely many boundary points. Okay, what do you know how they look like? Okay, can you think of a general pattern? When you trisect, what kinds of points do you generate? Very good. Yes. So those are the points that you see here. Okay. So this is what is happening. You start with length 1. In the next step, you take away 1 by 3. What you have is total length 2 times 1 by 3. In the next step, 2 square times 1 by 3 square. At the nth stage, you have n intervals, 2 to the n intervals of total length 2 to the n times 1 by 3 to the n. Where does this go to as n goes to infinity? So that means that intervals that you see, all of them have length 0. Okay? How many intervals do you have countable? Many intervals, right? At each stage you have 2 to the n intervals. So what is happening is you have taken away everything as far as length is concerned. Right? As far as length is concerned, you have taken away everything from the interval, still you have countably many points left. Okay? So this was a breakthrough in the sense of understanding how, you can construct sets. Now, why is it self-similar? Why is it like a fractal? I'll come to that later. But at this point, you see, what do you see? You zoom in, you zoom in, you zoom in, you see same thing, same picture again and again, right? So self-similarity is there. Now, differentiability, even though I don't want to talk about it, but you have a curve which have so many breaks, right? Breaks everywhere. So that also falls apart in some sense. Okay? So it sits in dimension 1, right? Because it sits as a subset of R and its length is 0. Okay? What do we mean by length here? The total length, which is 1 minus whatever you have taken away from there. Okay? At this point, think of length like that. Second example is the famous snowflake, known as Koch snowflake. Okay? And how is it constructed? So you start with a triangle. Okay? And I want you to look at each side. So what I'm going to tell you is what is done on each side. So just take one of the sides. That's the first picture there. You divide it into 3 equal parts and take away the middle part and replace it by a hill, a triangle. Okay, that's the second picture. In the next stage, what you do is, you have now 4 edges, right? In the second picture, you have 4 line segments joined together. On each line segment, you do the same thing. You divide into 3 parts, replace the middle part by a triangle. So in the second step, you can see each edge on the second picture is replaced by the second picture, but scaled down, right? What is the next picture? You have so many edges, right? On each edge, you replace it by the second picture, but scaled down, right? In fact, if I start with an equilateral triangle and I'm attaching equilateral triangles, you can do what we were doing in the Cantor set. How many triangles are there? How many pieces are there? And so on. So it's a nice exercise, fun exercise to figure out how many additional triangles you are adding, what are the areas that you are adding, and so on. So but what happens eventually is that you are adding more and more, right? So in terms of area, what do you think the area of the resultant picture would be? Greater or smaller than this? Greater, right? What about the perimeter? So let me go to the picture at the back. So you get a picture like this in the limiting sense. Forget about the triangle, boundary of the triangle, because that's not there. So you have a picture of which looks like snowflake, right? Can you guess the perimeter of it? Do you think it will be some finite number? Okay, you're adding something every time, right? But you know that there are, so it's like a series, right? Series of numbers. It can also converge, right? Need not diverge. When you're adding something, you can add in a way that the series converges, right? So that's not an explanation, right? You have to ensure that what you're adding is not keeping it bounded, right? It is making it diverge. And indeed that happens. The perimeter of the resulting object is infinity. And you can check it. It's very simple geometric exercise in geometry. You just have to do what? You just have to keep on looking at what are you adding each time, right? So it is an object which has perimeter infinity. But if you look at it like this, okay, each edge of the snowflake, it's an example of a continuous curve in which tangent cannot be drawn at any point. So there are corners everywhere. And this is how this example came about. So Koch wrote a small paper with this construction of a curve which has this property. Okay? So there's an algorithm. You have an algorithm to construct a function, right, which has this property. So I've given you an example. Yes. Limiting. We are looking at the limiting thing. Yes. Next example is what is known as Sierpinski triangle. Has anybody heard of this? Okay, some of you. Okay, so this is another example of a man-made fractal. And let me take you to this picture where the iterative scheme is given. So we are so comfortable with iterative scheme today. So I'm going to give you another iterative scheme which is not of numbers but of objects. Okay, so you start with a triangle. You look at the midpoints of the, so let's start with an equilateral triangle, okay? So on each side, you look at the midpoints and you connect them. So you get a triangle which is the red triangle sitting in the middle, right? Take it away. Okay, so you take away the red piece, you have three white pieces, right? Left, which are the top triangle and the left triangle and the right triangle, right? So in each of the three pieces, you repeat the process. You identify the midpoints, draw these green triangles. Okay? You take away these green triangles. So you have taken away the red triangle, you have taken away the green triangles. How many triangles are left? 9 triangles. You do the same thing again. You look at the midpoints, join them, you get a triangle, remove the middle triangle, and keep on doing this forever. So again, the limiting set, will it be non-empty? Yes. Why? So which points can you guarantee that they'll be there? The vertices, right? Vertices will surely be there, right? And you can actually give an argument like we did in Cantor set, 1 by 3 to the k kind of argument, but they look little different, but you can get something like that. So the resulting object that you get is known as Sierpinski triangle. And can you guess its area? So you can try that, okay? It's not a difficult exercise because you are taking equilateral triangles, you're taking its area, dividing by 4, taking it away, right? What you're left is 3/4 time what is there, right? So it's a very simple exercise to figure out what the area is. But anyway, this is another example of a fractal. Why is it looking like a fractal? Because if I zoom in and in and in, I see Sierpinski triangles everywhere, right? So what is the key feature in all these examples? Self-similarity, right? We constructed in a way that they look self-similar. The resulting object is self-similar, right? So the question is it the human nature to draw self-similar objects? So when we look even art, works by artists and so on, many of the art forms that we see have similar looking patterns, right? That are in a painting that you see, for instance. Or it is an attempt to capture the regularities within the irregularities that we see in the nature. So we are able to, even though an object that we see is so irregular, our mind is able to figure out some regularities there, and that is what we try to put on paper. Okay, so these examples um, uh, were built in such a way that they were capturing the self-similarity aspect of, of how we see things, right? So let me talk about some history of fractals. So it started with this example. Have you heard of Carl Weierstrass? Anybody who has heard of this name? Okay, so you will, as if you are a mathematics student or if you're going to take up some mathematics courses, he will appear again and again and again. And this is the example that he gave, which is an example of a nowhere differentiable function. So you see corners everywhere, okay? Then Cantor, so that was in 1872. In 1883, Cantor gave an example of a function on 0, 1 whose derivative is 0 at all points except for a small set. And this small set was the Cantor set. So except for points in the Cantor set, the function is 0 everywhere. Okay? Then, of course, this construction that we talked about of snowflake, right? So that curve. So that curve was an example. It was a geometrical construction of a curve which is nowhere differentiable. So before 1904, the examples were not algorithmic. They were not coming from a construction, right? But this was actually a geometrical construction to construct a curve, okay? Then in 1920s, Fatu and Julia were looking at mappings on the complex plane. It means a function from complex plane. All of you are aware of complex plane C, right? Complex plane to complex plane. Okay, so one example is you can take f of z equal to z square. Okay, so it just squares the complex variable. Okay, this is one example. So they were looking at mappings of complex plane and they were seeing fractals to appear as they were studying how these maps were behaving. Okay, that was one place where fractals appeared. And then there was an attempt to formalize fractals, even though fractal geometry was still not there. Okay, so people were understanding fractals in a very heuristic way, which was something which looks self-similar and lots of corners, right? Irregular. So Hausdorff tried to come up with a concept of dimension for subsets of Rn. So I'll talk about some of it later. And then there was an attempt to formalize the property of self-similarity by Paul Levy in 1938. But none of them are actually called fathers of fractal geometry, even though they have deep contributions. The father of fractal geometry is Mandelbrot, and somebody said Mandelbrot said. So Mandelbrot There's a lot of debate as to whether he should be called the father of fractal geometry or not, because there were path-breaking contributions even before that by Julia, Fatu, these examples, and so on. But he had access to computers. So this we are talking about in 1970s, right? So he was a mathematician at IBM Research Center, and he had access to computers. And what he could do is he could actually look at these maps and understand them on computers, right? So in the exercises that you have been doing, worksheets, we are asking you give 2 iterations, give 3 iterations. But when Dootika took over, she was talking about 6 iterations, 20 iterations. Why? Because she was working on a computer, right? But by hand, you would not do that. So he had access to computers, so he could talk about those iterative schemes, but he could talk about much finer details because he could run many iterations, which were not possible by hand. So he had that ability to work with computers, and therefore he came about with lots of finer details which theoretically could not come up before this. Okay. And he also came up with Mandelbrot set and so on, which I'll talk about later. And the word fractal comes from a Latin word, which is fractus, which means fragmented or broken, which is how we kind of understand the word fractal, right? The question is, how do you measure them? So we talked about Cantor set, right? Cantor set has length 0, right? What do we do with it, right? It has length 0. What more can we do with it? Can we understand how big it is, right? In terms of number of points, right? So when we understand an object, we think of it, if it's a one-dimensional object, we think of length. If it's a two-dimensional object, we'll think of area. If it's a three-dimensional object, we looked at volume and so on, right? So now Cantor set has nothing, right? Even Sierpinski triangle has nothing. So how do we understand them? So let me give you one approach which works in very specific cases. But let us understand what we mean by dimension. Okay? So can somebody tell me what do you understand by dimension, the concept of dimension? Don't give me linear algebra class definition, okay? Yes. So if your set is sitting inside R, for example, already you know that it's sitting inside R. Can it have dimension more than R? You don't expect that, right? Sitting in R2, what do you expect? Less than 2, right? Can it be less than 1? Can you give me an example of a subset of R2 which has dimension less than 1? Sorry? Point, yes. Right? So, but it cannot exceed 2, right? Okay. So, let us consider, let us understand what dimension is capturing. So, consider a line segment of length 1. Okay. And let us scale it by 2. What do you get? So you start with a line segment of length 1. So let me call it interval 0, 1. If I scale it by a factor of 2, I get interval 1, 0 to 2, right? So how many copies of L are sitting inside this new object? Perfectly. 2, right? There are 2 copies. So in this particular case, the number of copies that you get is same as the scaling factor, right? So n is equal to s, right? So this we know is sitting inside R, right? So it is already in one dimension. Let us go to a square. So if you take a square of unit side and you scale it by a factor of 2, what do you get? So let's say it's based at 0, 0. And you scale it by a factor of 2, what do you get? Square of side? 2, right? Right? How many pieces of, how many times you see the original one inside it? What is the relationship between n and s? N is equal to s square, right? What was 2 here? The dimension, right? Let us go to a cube. What happens? 8 times, right? I hope you are not borrowing the pattern, but you can actually see that you get 8 cubes. I hope you, all of you can see there are 8 cubes. That's what happens, right? So what is the dimension picking up? This is the expression that you expect in the number of copies when you scale something. But this is of course very limited. It works for self-similar objects. So upon scaling, you can write the scaled object as a union of original object. Okay. For instance, if I take a ball, a circular disc in R2 and I scale it by any factor, I cannot write it as a perfect union of smaller discs. Do you believe that? Okay. So intuitively we understand this, but it's again an exercise for you to solve. That you cannot write a disc, circular disc, as a union of smaller discs of same radius. Okay, you can try this. So what is the pattern? Pattern is if you have a magnifying or scaling factor and S, and N is the number of copies of the original object that you see in the scaled objects, then the dimension satisfies this formula, right? So if I take a self-similar object, what is a self-similar object? Self-similar object is one that there is certain scaling S such that you see same object again and again, which happens for line segment, which happens for square, which happens for cube. Okay? So if that is the case, then you want this to be the formula, right? So if I take log on both sides, D comes out to be log n by log s. And this is how we define dimension of a self-similar object. Borrowing the ideas from the concept of integer dimension we know. But the challenge is to identify suitable scaling. Okay, that is the challenge. So let us look at some examples. Cantor set. Okay, so now you know what Cantor set is. So Cantor set is you take the interval 0, 1 and you break it down into 3 pieces. You remove this part, then you remove this part, you remove this part, and so on, right? What is this point? 1 by 3, this is 2 by 3, right? So if I scale this by a factor of 3, so let me just put 3 here, even though, so there are different scales. So 1 has gone to 3. Where will 1 by 3 go to? Where will 2 by 3 go to? So this part is not there, right? Isn't it? What happens here? You see the same picture, right? Isn't it? So in the new picture, how many Cantor set are sitting? Here you don't have any. So you have one inside 0, 1 and one inside 2, 3. So how many are there? 2. So if I use the formula that I have, This should be the dimension of the Cantor set. Okay, it's a number which lies between 0 and 1. It can't be more than 1. Why? It's a subset of R. Yes. Sierpinski triangle. So in fact, mathematically speaking, a fractal is an object whose, if it's self-similar, it's an object whose self-similarity dimension is a fraction. Then we call it a fractal. Okay. So a line segment, we don't call it a fractal. Square, no. Cube, no. Okay. So Sierpinski triangle, what happens? If I scale it by 2, how many copies of Sierpinski triangle do I see? 3. Okay. It has to be a number less than 2. Can it be less than 1? Why? Not this number. This number you know is not, but why should it be more than 1? Because it's growing in both directions, right? So you need 2 directions to define it, right? So it's not, I mean, you need more than 1 direction to define. I should not say you need 2 directions, but you need more than 1 direction. It's not growing in linear fashion, right? Snowflake, if I scale it by a factor of 3, I see how many copies? 4 copies, right? Okay. In all these cases, S was crucial, right? I had to identify S, the proper scaling, so that the original object is sitting inside it as copies, right? So this I will leave as an exercise. I will give you a hint. Can you construct a fractal which has dimension between 0 and 1? So I give you a number between 0 and 1, d, little d, and can you construct a fractal with that dimension? Okay. And let me give you a hint, which is that when you were constructing Cantor set, you were removing the middle third part, right? Now I'm saying instead of middle third, you delete the middle part whose length is delta for some fixed delta. So in Cantor set, delta is equal to 1 by 3. So I'm saying you take some other delta and you keep on doing this process. So for suitable delta, you can come up with a dimension which is d. Okay. So this is it requires a few steps, but it can be done. So in fact, you can construct fractals of dimension any positive real number. I give you a positive real number, you can find an algorithm to construct a fractal, and it uses Cantor set construction. So it's a very powerful construction, and we use it all the time in mathematics. So now that I have given you the answer, given any positive real number, you can find a fractal with that dimension. So yes, there is a fractal with dimension pi. There's a fractal with dimension e. There's a fractal of any positive real number as the dimension. It uses, if you understand Cantor set construction, you can produce this. And this can be very good, exercise when you're getting bored and you want to do something fun. You can work out these exercises. And if you have younger siblings, they would also be interested in these activities because they use very elementary kind of ideas. Okay. So what have we achieved so far? We have just defined the concept of self-similarity dimension, but it can be used only for limited objects which are self-similar, right? Now question is, what about other objects? So since I have just 11 minutes, I will not go into the dimensions. So I'm going to skip all of this. But there are several concepts of dimensions which is using what are known as covers. So if you're interested, we can talk about it. But let me come to some techniques to produce fractals. Okay. So these techniques are iterative techniques, right? So one of the techniques to produce fractals is, so this technique is known as the chaos game. Okay. So what am I going to do? I'll start with any point in a triangle. So these red, green and blue are the vertices of the triangle. So I'm not drawing the edges. Okay. So you have 3 vertices of the triangle. You start with any point in the triangle. So I've called it seed, right? So that is the starting point. Now you roll a fair die. You have 6 possibilities, right? So if number 1 or 2 show up, then you move towards the green vertex. If numbers 3 or 4 show up, you move towards the red vertex. And if numbers 5 or 6 appear, you move towards the blue vertex. Okay? And you go halfway. So for instance, if the first time you get either 3 or 4, you are going towards the red vertex. So I start from here, I join this point and red vertex and I go midway. Okay, so I'm here. Now I get green, right? I get either 1 or 2, so I go towards the green vertex. So I join this with the green vertex, I go midway. Next time I go towards blue, so I go midway. Once I am here, I again go midway towards blue. So suppose you keep on getting blue again and again, where will you converge? To the blue vertex, right? So you are coming closer and closer and closer to B, right? But you can have anything, right? You can have R, G or B because you are tossing, you're rolling a fair die, right? So with every rolling of die, you are producing this sequence, right? So if all of us are rolling die and recording the sequence, we have close to 80, 85 odd sequences, right? So you have those many orbits there, right? Put all of them together. The final, okay? So suppose you do this 10 times, okay? You look at where you are finally. So you have 85 points on the triangle, right? Which are the final points where we have reached. So can you guess what is going to happen if you do this? A wild guess. Hint is you'll get one of the objects that you have seen. You're going midway, you're going towards the corners. Which fractal did we produce from triangle? Sierpinski triangle, and that is indeed what you will get. Okay, so you will get this. So it's a, if you are comfortable with programming, you can try it. So you are playing this game where you're starting off with a point and doing this thing, right? And you do this multiple times and you consolidate your results, put it here. This is the picture that you will get. What are the extreme points? The vertices correspond to which sequences? R all the time, right? Will give you the top vertex. G will give you the left vertex, green vertex, and B will give you the right vertex, right? Because you're converging there, right? So you can construct Sierpinski triangle by playing this game as well. So a lot of fractals can be built using such a scheme. There's another way of constructing fractals which is known as iterated function system. So I'm not going to get into the theory, but all of you have seen the picture of fern, right? The first few pictures that I had shown. So you can construct a fern using a computer, and it requires these 4 maps. These are not linear, but there is an addition of a vector, right? So these are called affine maps. So it is like AX plus B, right? So these are called, if B is 0, it's a linear map, right? You all see that in linear algebra, and if B is non-zero, it's an affine map. So if you run all these functions, 4 functions with certain probabilities on computer, I've given you the probabilities. So the probability of the first function, choosing the first function is very small. Even for the third and the fourth, the second one has highest probability. So I'm going to choose second again and again and again. And the picture that it produces is this. Okay? And what is the contribution of these maps? The first map produces the stem. The second map produces the smaller leaflets. And there's more contribution because there are smaller and smaller and smaller leaflets, right? So you need more and more of this map being used. Then F3 and F4 produces the left side and the right side. So it's basically produces this largest one and this largest one. And then the second map basically translates it and scales it down. And then keeps on scaling it down. So you get this kind of picture. So this is another technique to construct fractals. Iteratively. So for instance, on a computer, I'll take a bounded region in R2. I start with a seed, any initial condition, and I keep on applying these maps, and I look at the final where I stop, right? So let's say you are running it 1,000 times, you see where you stop, and you run this many, many times, and you collect all those points. So in fact, I can tell you mathematically what this object is. It is, let me call this capital F, the object that you see on the bottom. F is equal to F1F union F2F union F3F union F4F. So F is the set for which if you apply F1, F2, F3, F4 and take their union, that is equal to F. It produces this. So there's a mathematical background where you can prove existence of this F, but on computer, what will you do is what I told you. But you have to run it enough number of times to make it work. So Mandelbrot set, which somebody mentioned in the beginning, is one of the famous examples of fractals, which is still, lots of things are still unanswered for Mandelbrot set. So it is generated by this map, which is on the complex plane. So I wrote down this example. So instead of this, just add C here. So Z is a complex number and C is a complex number. So if C is 0, the map is Fz equal to Z square, right? So what do I want to do with it? I start with the point 0. So my initial condition is always 0. Okay, my x naught is always 0. And I keep on applying this map again and again. So suppose C is 0. What is this map? This map is Z goes to Z square, right? If I start with 0, where will 0 go? What is 0 square? 0, 0 and so on, right? So 0 will never move. If I take Z square plus 1, I start with 0, what do I get in the next step? 1 in the next step, and so on, right? So it seems to diverge. Whereas if I take, let's say, some half, then you can also again try to see what's going on. So where the trajectory is going depends on what C is, right? If C is 0, you don't move at all. If C is 1, you seem to diverge. And you can also find values of C which are less than 1 where it seems to converge. So what is Mandelbrot set? Mandelbrot set is the collection of all those C's where you don't have divergence, where the orbit is restricted. So for instance, 0, C equal to 0 will be there. But C equal to 1, will it be there? What is the orbit when C is 1? It's diverging, right? So C equal to 1 is not there. And this is the picture that you get. So this black region is the, so it's sitting inside C, and it is the collection of all those little C such that the orbit of 0 does not escape to infinity. Okay, it stays in a bounded, it's bounded, that sequence is bounded. It's a sequence of complex numbers. You're used to sequences of real numbers, but now I have sequences of complex numbers. So when will you say that a sequence of complex numbers is bounded? I'll just take 2-3 minutes. So when will you say sequence is bounded of a complex numbers, of sequence of complex numbers is bounded? Modulus, right? When you take modulus, it is now a real sequence, and then you know the notion of convergence. This is what you get. Do you see the boundary? Right? And this is the famous boundary, which is well studied in mathematics, and still there are so many things that we don't understand about the boundary. So these are some zoom in images. When I zoom in on the boundary, these are the kinds of pictures that you get. And it turns out that there is a concept of dimension, which the dimension comes out to be 2 for a Mandelbrot set, the boundary of Mandelbrot set. So it's a curve, right? But it has dimension 2, exactly 2. So it is, from the mathematical definition of fractal, it's not a fractal, but it is like a fractal. It has all the other properties of fractal, which is self-similarity, but not like Cantor set. So self-similarity is not like Cantor set. You zoom in, you see pictures which only resemble the old picture. It does not resemble completely. Okay? So there are newer and newer features that people see as you zoom in to the boundaries. And Mandelbrot set could come up with these pictures because he had computers, right, to keep on zooming in to the boundary. So I'll end with a quote by Mandelbrot, which says that fractal geometry is not just a chapter in mathematics. It helps every man to see the same world differently. So I'll stop here.
Any questions?
Yeah, scaling dimension only works for self-similar objects. So Mandelbrot set is not self-similar. So Hausdorff dimension is defined for every bounded subset of Rn. Yeah. Yes, absolutely. So it generalizes self-similarity dimension. It generalizes the dimension definition that you know from linear algebra. Yeah. Yes. Okay, so you're saying, can you model, if you are given a picture of fractal, can you model it? Can you find equations? I don't know how to do that, but maybe, like for instance, if I give you Sierpinski, okay, you can take it as an exercise. Take the Cantor set, forget about Sierpinski. Can you find 3 equations? Can you find 2 equations which determine the Cantor set? Like Fern that we constructed using 4 maps. Can you find 2 functions from R to R? Okay, so let me write it down. It's a very nice exercise, and thanks for asking this question. So So if I take Cantor set C, let me call it C, produce F1 and F2 from 01 to 01 such that F1C union F2C is equal to C. You can do the same for Sierpinski triangle. You can find 3 affine maps on R2 such that F1 of the Sierpinski triangle using F2 of Sierpinski triangle using F3 of Sierpinski triangle is actually equal to Sierpinski triangle. So they are coming from iterative function scheme, but not every fractal comes from there. Okay, these fractals do come. No, no, no. It doesn't always produce a fractal. For instance, if I give you a linear map fx equal to 2x, okay? There is a not necessary and sufficient condition, but there is a sufficient condition which guarantees that you will get a fractal. And those are basically the coefficients of, it has to do with the first derivative in some sense, okay? So whatever you are learning here is very relevant to do this. Yes, so a lot of, I don't know if you have heard of MC Escher, but his paintings are inspired by fractals. So you see these going up and going down stairs together, kind of. So in his pictures also you see this concept of fractals. But then there's also in topology, in actually every area where fractals are being used. So one of the examples I can give you, because we are on applications, there was an antenna, I don't know the, I don't remember the name of the person who created, but there are antennas which are in the shape of fractals. So what you do is you basically construct a tree. So you go like this, then you construct like that, and then you do this. So within limited area, you are going to infinite perimeter, right? So that increases the receptivity of signals. So there were these things which were constructed using fractal ideas. So this kind of finite area but infinite perimeter is quite useful in building up things in real life. Yeah, and these are used. I saw them, and actually when I was preparing this talk, I was not, I had heard of this, but even in electrical books, engineers read it. Neural networks, yes. So in neuroscience, uh, one is people are trying to model the neural systems using fractals. Yes, yes, absolutely. Yes. So there is a, it also relates to cryptography. So I don't have so much time to talk about it, but like you said, 3 maps determine this, right? But Fern can be produced using 4 maps, right? So you just need 4 numbers, 0, 1, 2, 3, and produce it, right? Sierpinski triangle 3, right? So those numbers are important actually.